So now moving on to our next question, which is path sum 3. So basically we're given the root of a binary tree and an integer target sum, and we need to return the number of paths where the sum of the values along the path equals target sum. So the path does not need to start or end at the root or a leaf, but it must go downwards, that is traveling only from the parent nodes to the child nodes. So basically the condition given to us is that we have to return the number of paths where the sum equals target sum, and we can start from any node and end at any node, given that we only travel from a parent to a child, right? So we cannot traverse up. Instead, we need to traverse down only. Okay, so that's the precondition given to us. And let us see for this example. So let us build the tree first. So this is the tree, and let me show you how we build it. So basically 10 we have first, then we have 5, then we have -3, then 3, then we have 2, right? Next we have null. So basically the left child of -3 is null, right? And then we have 11. So we're going level by level and filling all the values in the tree. Then we have 3 again here. Then we have -2 as the left child, right child of 3. Then we have null. So basically this is null, and then we have 1, right? So this is our tree. Null means that it does not exist. So this is the tree. This is the exact same tree that is formed here, right? So now we need to calculate the target sum equal to 8. It's given 8. So we need to check for all the paths that have target sum equal to 8. So we traverse from up to down. So basically from the parent to the child. So in this example, you can see -3 plus 11, that gives us a target sum value equal to 8. So this is one path. Then another path would be 5 to 1. This also gives us the sum 8. And then 5 and 3 again gives us 8. Now there would not be existing any other paths other than this from parent to child to get a target sum equal to 8. So we return the counter as 3, right? So the paths that sum up to 8 are 3 paths total in this tree. Now we have this example. So let me show you this example for better clarity. So we have 5, then we have 4, then we have 8, then we have 11, and we have null here, so that we don't draw. Then we have 13, then we have 4, then we have 7 and 2 as the left and right childs of 11, and then we have null. So 13 would have no left and right children, and then we have 5 and 1, right? So basically this is our tree that has been given to us, and target sum is given to us as 22. So we need the target sum as 22, and we need to return the count of paths that can exist. So basically let us see, 5 plus 8 plus 4, 5 plus 8 gives us 13, right? Then we have to add plus 4, that gives us 13 plus 4 gives us 17, and 17 plus 7 gives us 24. So we don't take this path, instead we're taking this path, that is 13 plus 4 up till here, that means 17, and plus 5 gives us 22. So that is equal to the target, you see, right? So this path is considered. So this is our first path that we consider, right? Then here we can't go because 13 plus 13 would give us 26, so that would exceed the target sum, so not forming the target sum. We can try for 8 plus 4, 12 plus 7, that is also not equal, 19, that's 19. So now let us go towards the left part. So 5 plus 4 gives us 9, plus 11. 9 plus 11 gives us 20. Now 20 plus 2, you see, 20 plus 2, 22. Again, one more path we have received. So we have till now we have two paths that sum up to target sum equal to 22, and we are starting at the root node. Right now we can try for this path as well. That is 4, 11, and 7. So you see, 11 plus 4 is 15, and 15 plus 7 again is 22. So basically, again another path is found, and we have not started from this path from the root, right? Now, in case there were some other values, we also are not necessarily having to stop at the leaf node, because the condition is given that it is not necessary that we start at the root node or end at the leaf node. We can have paths that sum up to target in the intermediate or the internal nodes as well. So right, the answer was 3. So basically, let me now just take you over to the intuition. Right, so this is my solution. Firstly, we are going to be applying BFS and DFS. So BFS is to iterate over every node of the tree. That is, each node is treated as the starting point of for the, and DFS we do for each starting node to explore all downward paths and count the number of valid paths that sum to target sum. Now our algorithm explanation. So outer BFS is in which we use a queue to perform BFS traversal for all nodes, and for each node call the count function to count the number of valid paths starting from that particular node, right? Because there are conditions where the root is also, it's not necessary that the path comes from the root itself. There can be another internal node, so we need to count the number of paths using the count function. And the count function is basically the DFS, where we recursively explore left and right subtrees, decrement the target value by the current node's value, right? And if the target becomes 0, that means that we have found a valid path. This means because the current value, that is the node's current value, target minus current, if that equals 0, and we are doing this recursively, that means we have reached a path which has the sum equal to target, right? So we found a valid path starting from the current node, and we need to continue exploring because there may be additional valid paths in the children. So this is our overview, what we do. Now some details. So paths can start at any node, but they must go downward, parent to child. we must explore every possible every possible starting node, and the count function is called for each node. Now let us discuss the time complexity. So in the worst case, we have O of n square, because BFS would visit n nodes, right? But for each node, DFS, that is the count, can take up to O of n in a skewed tree. So this is basically a skewed tree in which we have only let us say left children only. So the height of the tree becomes equal to the number of nodes, or it could also be towards the right, right? So this is a right skewed tree and this is a left skewed tree. And best case is for balanced trees O of n log n, when we have the height equal to O of log n, right? And BFS basically is called for every node, so it would be n times log n. So this is a balanced binary tree, and the height equal to n, log n, only log n, right? So this is the time complexity, and for the space complexity, we using DFS count DFS function. So for recursion depth O of h, where h is the height of the tree, and O of n for the BFS cube, right? So now let us get to the most important part, that is the coding part. So basically, path sum is our function, and count is our DFS function. So count basically counts all paths starting from root with the sum equal to target. So this is our function which takes root and the target, which is in long format. So if root does not exist, that is, if root is equal to null, we return 0, because then there would be no path starting from root, because root itself does not exist. So our answer would return 0. Otherwise, we calculate the remaining value, that is target minus the current node's value, that is root's value at the moment. We'll call this recursively later. So target minus root value is our remaining after visiting that node, right? So this is the remaining. Now we check if the remaining has been equal to 0, has become equal to 0. That means we have encountered a path in which this target sum has been achieved by going over all the nodes in that particular path, right? So if rem is 0, that is current node completes the path, but we still continue to find further paths. So we basically, one path has been received, so we return 1, that is the count of this particular path. But since there can be more valid paths in this particular from this particular child or this particular child or this parent itself towards the left, right? So there may be a condition, right? So that is why we add it recursively, that is count of root ka left. So we're going towards the root ka left, remaining value, pushing passing that, and also recursively taking it from the root ka right and passing remaining. So basically, one path has already been received, so we return 1 plus this value. Otherwise, if the remaining value hasn't reached 0, that means we still have to consider more node values in order to reach our target sum. So we continue exploring our children, and we don't add 1 here. So we just explore our children by count route of going to the roots left recursively and calling this function for the right as well recursively. So that is our DFS function. Now moving on to the BFS. So for every node, count the paths starting from that particular node. So path sum is equal to basically path sum takes the root and the target sum as parameters, and we set a counter equal to 0, which will count our total number of paths. If the root is not null, then we return 0. Sorry, if the root is null, we return 0. That is because if the root itself does not exist, the tree won't exist, and the path sum or the counter of the path sum would be 0, right? Now we declare a queue of node star type, standard BFS template, and push the root in, and some we have a integer variable here. So while the queue is not empty, we extract the node from the top of the queue, sorry, the front of the queue, right? So the node we extract from it and pop it out, pop this element out, set the sum equal to 0, and call our DFS here, that is counter plus equal to count of this the node that we're passing, the node that we have taken out from the queue, and the target sum. So we basically using this, we count all paths starting at this node. And since we are going for n nodes, and DFS is basically, in the worst case, we have n, right? That is a skewed tree. So this becomes an overall time complexity of n square. And the best case would be when we have a balanced binary tree. So that would mean that our DFS function is taking O of log n, because the height of the tree is log n, and our basically this runs for all the n nodes, right? So the best case time complexity would be O of n log n for balanced binary trees, O of n square for our worst case, which is the skewed trees, right? So once we've done this, we check for the nodes left and right if they exist. If these left children and the right children, if they exist, we push them into the queue for further processing. And finally, when we come out, we return the counter, that is the total number of paths that have a path sum equal to the target sum. So that's it. And now moving on to our DFS function. So this is only using DFS. So the path does not need to start or end at the root or leaf. The path must follow parent-child connections. The key idea is to use for this DFS only function prefix sum to keep track of the cumulative sum from the root to the current node, and hash map and unordered map to store the count of each prefix sum encountered along the current path, right? So for each node, we are computing the current sum from the root, right? So then we want to find if there's a previous prefix sum such that current sum minus target sum is equal to previous prefix sum. This means that the subpath from the previous node, from that particular node to the current node, has a sum equal to target sum. Now we store prefix sums in path count, where key is the prefix sum value. So basically, in path count we have prefix sum value, prefix sum, and the value is number of times the prefix sum has been seen. This sum has been seen on the current path, right? We use DFS to explore all possible paths in the tree. So now let us go to the algorithm. So our algorithm is something like this. Firstly, we check for the base case. If the node is null, we return 0. Update the current sum, that is current sum plus equal to root's value. Check for valid paths. Look for current sum minus target sum in the path count map, and increment the path count of current sum to indicate that this prefix sum is now seen. Because for left and right subtrees, since we're using BFS only, and backtracking, decrement path count of current sum before returning to ensure it is not used outside the current path, right? So time and space complexity, O of n, it would be, because each node is visited once and hash map operations are O of 1 on average, and space complexity is O of h plus n. For O of h, that is the height of the tree for recursion stack, and O of n for the hash map in the worst case, that is when we have a skewed tree. Now this is the function, so let us go through it. So we declare our helper function, which is our DFS to count paths, which takes root, target sum, the current sum, and the unordered map of path count, which stores the prefix sum and the number of times we have seen it in our current path. So if root is null, we return 0, and current sum, in that we add our root's value, that is the current node's value, to the prefix sum. Then count the number of paths ending at current node that sum to the target. So in count is equal to path count of current sum minus target sum, and then we include that current prefix sum in the map, and then we call our recursion, that is count plus is equal to helper of roots left plus helper of roots right. All the other parameters remain the same, right? So we are recursing to our left and right subtrees, and backtrack now. Remove the current prefix sum. That is important for going over the sibling paths, that is these paths, right? Siblings are on the same level and are connected by the same parent. So path count of current sum minus minus, we backtrack, and we finally return the count. Basically, in our main function, we are taking root and the target sum, and on our map we have declared for path count. And the base case is that one path exists with sum equal to 0, that is initialize path count of 0 is 1, and we return our helper function, in which we are passing current sum as 0 and target sum as it is.